Starting from fallacy number 1, the network is reliable. Now, the thing about this fallacy, and a lot of these fallacies, is that if I asked any of you point blank, do you think that the network is 100% reliable all the time? Nobody would say yes. We've all experienced all sorts of hardware issues, security issues, firmware issues that cause connectivity to drop in a production environment. We're aware of all of that cognizantly. But when it comes time to write code, we've probably all written code that looks something like this, where we're newing up some proxy to some remote service, invoking some method on that proxy object, passing it some data, and then getting some response back from it. Who's written code like this before? Yes? Pretty much everybody. Good. So we're aware somewhere in the back of our mind when we're writing that there's lots of magic happening behind the scenes here. That there's the marshaling of this data in invocation into a wire accessible format, serializing the data, dispatching it to the other side, deserializing, dispatching, invoking the code, getting the response object, serializing the response object, dispatching that across the network. All of that stuff, we know there's a lot of magic that happens here. And again, we're aware that there's a remote call happening here and all of these bad networking issues can hit us. But the reality is we don't really think twice. There's this sort of simple, agile mentality of the, well, it works on my machine. Check it in, passes all the unit tests, right? So what's not to like? But the thing is, when we think about compilation and unit tests and all those types of things, usually they're evaluated on a single machine, right? We don't run those type of big, heavy tests in a distributed environment. And the thing is, again, even in a distributed environment, this will work most of the time. But that's the issue. It's that except when type of scenario. So what happens if when invoking this code, we get some type of HTTP timeout exception? That's where the problems kind of start. Is, well, we've done an invocation, we have some data, we need to get that data to the server. We sent an invocation, but now we're kind of in this in-between scenario. Because maybe the server is still processing that request, right? This could be some sort of long-running workflow that it's running, and it just timed out. Doesn't mean that the data's gotten lost, but maybe we just didn't get a response. On the flip side, it could be that the timeout occurred on the way to the server, right? Maybe the data didn't even arrive. And if it didn't, well, that's kind of a problem because this is important data and we need to get that to the server. But now, as a client, it isn't entirely clear what we should do, right? We've sent some data to the server. Maybe it has it, maybe it doesn't. So what do we do about these problems? Anybody? What do you do about these problems?
We should have a look at the error codes because they're going to get a HTTP error of some sort. And that can help identify what the issue is.
Okay, so if we get an error code that tells us this was a timeout, we're still in that scenario of, well, maybe the server has it, maybe it doesn't. And I mean, we can try various types of solutions. One of the common things that developers do anytime something goes wrong is not always retry, but that is where we're going. Usually something goes wrong, developers log it, right? Something bad happened. Let's write to the log and say that something bad happened. Some of the better solutions are to actually retry it on the server side. Some of the poorer form of solutions is to throw that error in the face of the user and say, hey, something bad happened. You figure it out.
Strategy must be conditional based on what operation you're doing. If you're doing a synchronous operation where the user expects some response right away, then you have to handle it in one way, and an asynchronous
absolutely.
It's quite
right.
A different story.
So if we're in an asynchronous scenario like you described, is usually when we don't have a result that is going to be coming back. And then there's a more natural type of scenario where the user is not waiting actively for something to happen, and then the system can retry in the background and the user remains oblivious. So like you said, in the asynchronous scenario, things can be quite simple. In a synchronous model, like the traditional request-response pattern that is used so much, then we're kind of in this in-between scenario where the user, well, at least we've designed the system in such a way, assuming that the user is waiting for a response. And then even if we retry, then once again, we're in the scenario of, okay, well, the user is still waiting for a response, right? Now, once you start down this path of saying, all right, let's build some sort of strategy, as you were saying, things start simple, but they kind of get a little bit more complex gradually. Is that, okay, we'll do a retry in the case that we didn't get a response, and then there will be some sort of acknowledgement model that we're going to build on top of just sort of the basic retry. If it's in an asynchronous type of scenario, we'll do some store and forward functionality because we no longer need to return the result, and therefore we can asynchronously move things along a longer pipeline. And once we start going down this path, then while this works fine when all you have is a single invocation, when you start dealing with multiple invocations, and that's fairly common, right? When you're doing some kind of integration between 2 or 3 other services, dare I say microservices, then transactional integrity kind of becomes a little bit tricky of the, well, service A gave me a response, service B didn't yet. What is the state of my system? And how do I make sure that I preserve all of the atomic, consistent, isolated attributes of the transactional integrity of a distributed system? Now, the thing is, if you're doing this on top of HTTP, you're always going to be almost there. There's always going to be the scenario of, this time I've done it. This time I finally solved all of the edge cases. And then some period of time later in production, some other thing will blow up and you'll discover, oh, except that bit. So this is the place where when you ask developers, so, are you done yet? And the developer will say, I'm 99.5% done. Anytime a developer uses a decimal point to describe how far away they are from being done, that's the point in time that you can understand they have no idea anymore. It's just that they said like 99% before, they have to present some kind of progress. I mean, if somebody asks you, are you done yet? You're going to be like, oh, I'm 90% done. And then they come to you a week later and say, what about now? Are you done now? You're not going to say I'm 80% done after saying that you were 90% done just a week earlier, right? Even though your understanding of the problem has increased during that period of time. And you may realize, actually, there is more work remaining than what I thought was remaining the last time you asked me. And that's why we use decimal points, right? That's our way of getting some free extra zeros at the end. But as a hint, A, try not to do that. Communicate more clearly that we've learned more about the problem, the estimate is bigger. And B, if you're the recipient of those type of estimates, anytime a developer gives you a decimal point in terms of how close they're done, that's the point in time that all estimates are off the table. You need to, in essence, go back to the drawing board and say, okay, tell me exactly what you've been doing. Where are we? What's left? And let's re-estimate from now, okay? So this type of, well, let's go build something on top of HTTP to make it more reliable. Too many edge cases. Don't waste your time on that. Instead, use some kind of reliable messaging infrastructure. There's a lot of choices out there. If it's on the Microsoft platform, you've got MSMQ, SQL Server, Service Broker. If you're in Microsoft's cloud, Azure Service Bus, Azure Storage Queues. If you're on the Java side of the world, there's quite a few more options out there. There's WebSphere MQ from IBM. Oracle has advanced queue technology. There's TIBCO. There's Apache. There's a lot of choices out there. And we'll get into some of the differences between them. The important thing is those 2 little letters at the end that say message queue. What's so great about a message queue? The big thing is that it's designed to solve these types of problems of building in the retry acknowledgement, store and forward transactional type of behavior. And yes, as I was saying before, that stuff is fairly complex. The important thing that we lose once moving to some sort of message queuing environment is request response. And that's really the conflict around building more reliable distributed systems. Because building unreliable distributed systems is easy. Okay? Anybody can do that. But if you're here in this class, we're going to be looking at things from the perspective of these things are actually supposed to work in production under severe stressful workloads and under all of the common conditions of, as we said over here, hardware failures, software failures, security issues, all that kind of stuff. So the issue then becomes, if message queuing is going to help us with the asynchronous parts of our communication, what do we do about the synchronous parts? And that's really where queuing in a lot of this class is going to lead us to, is that element of you're going to have to redesign and rethink some fundamental principles of how you do design and where you introduce network boundaries in order to solve the problem of the network not being reliable. So the thing about this fallacy is the network is not reliable. That's a given. Okay, you can't fight that. It's gravity. The question here is, can we build a reliable system on top of fundamentally unreliable networks? And the answer is yes, but we're going to have to build them differently than the traditional request response patterns that we've gotten so into the habit of building from building regular applications where everything was in memory. And we could just assume that every request would always have a response, or that the whole application would just crash altogether. So in this type of environment, given that request response is going to become a problem, it means that you're going to expect to see a whole lot less request response across the network. And that instead we're going to redesign a lot of the boundaries of our system in order that there will be more of a queue-based delivery model. And ultimately, that is how we're going to get reliability. Now, a number of years after this fallacy was originally penned, Martin Fowler, hopefully that name rings a bell to some of you, penned a law, if you will, of distributed systems or distributed objects. So the first rule of distributed objects is don't distribute your objects. All right? The second rule of distributed objects is don't distribute your objects. Okay? It's really that important, this type of request response distributed object model. And let's not kid ourselves. This is effectively what we're doing here. It's one object running on one machine, request responsing with another object on another machine, request responsing with 3 other objects on a whole bunch of other machines. You can dress this up. You can call it web services. You can call it REST. You can call it microservices. Fundamentally, it's distributed objects. So number one rule, don't distribute. There's no prize that you get from spreading your system over more machines. If anything, based on this fallacy and others that we're going to be talking about, the more machines you intermingle between your objects, the worse off things are going to be.